recording. Okay. Okay. Yeah. We basically characterize the Nyquist stability criterion, right? We find out that as long as we know the information of the open loop system, then we should be, well, specifically, we know the Nyquist plot and the poles information of the open loop system G of S, and then we're gonna be able to predict if this closed loop system is gonna be stable or not based on that information, right? So that's what the Nyquist stability criterion tells. Okay. Now, if H of S is not equal to 1, then your open loop system, you know, the open loop system is the loop transfer function, right? From here to here, right? So exactly. If H of S is not equal to 1, then apparently open loop system includes H of S. So the evaluation becomes GH, not G. Okay. So if H is not equal to 1, you cannot drop the H. You need to include H in the evaluation. You need to obtain but the principle is the same. You still get the poles of this transfer function. I mean, counting how many poles in the right half plane, and then you need to draw the Nyquist plot of GH, not G, right? So it's not a big deal, okay? But like what I said, normally we can use the scaling method approach to make the H of S to make the feedback system is a unity feedback. The loop transfer functions stability is not important. Okay, I mean in terms of the stability requirement, it is always like what I said. All the performance requirements are posed for the closed loop system. Okay, the open loop system, it's whatever open loop system. You got it. It's not up to you. Okay, but you could have a good. You could have a bad, open loop system. Okay, so what is more important is that after you apply the controller and obtain this through this feedback structure, so what is going to be the behavior of this closed loop system? That matters. Okay, that matters. So you should be careful about that. Okay, okay, yeah, okay. So, so what do you mean? What do you mean? I don't understand your question. Which one is not a open loop system? Because we include the feedback. You include feedback. Well, this is in the feedback channel, right? The H of S is in the feedback channel. But when we say feedback system, we mean that you close the loop here. You see, the open loop, why we call this one open loop? Because we break the loop here, okay? So if you break the loop, then this guy here, the signal here becomes the output signal, right? So your open loop is going to go through a G and through H to reach this point, but not feedback to the summing junction. If you feedback the signal to the summing junction, you form a closed loop, and that's the closed loop system matters. You see what I mean? So that's the difference. Okay, you know what? You need to go back to check the control 1's notes and to recall those definitions. Okay, this open loop or closed loop issues we talk about a lot. We defined it clearly in the control 1, so you need to go back to check those notes. Okay, I can't repeat too much here. Okay, so I've just used the concept, the open loop, the closed loop. Okay, all right. So now. Yeah, so I also mentioned that there is a very important special case. Is that when the open loop system G of S, it's stable. Okay, well here you can understand here we imply that H of S is actually equal to 1 here. Okay, right? So we only need to check G. If H of S is not equal to 1, check GH. So if this open system G of S is stable, that's actually a special case, but that is a very important special case. Okay, so in this case, we know that the P is not equal to if P is straightforward equal to 0 because there's no right half plane open loop poles, right? So you can see that the stability, the N in this case is going to be equal to Z. Okay, so the stability criterion then can be simplified to what? To just like you check if the G of S's Nyquist plot is gonna encircle the -1,0 point or not on the G of S way, right? Okay, so we talk about that. So this in this case is straightforward. You just need to see if there's any encirclement. If there's no encirclement, closed loop system is stable. If the encirclement happens, yeah, the closed loop system is not stable. Okay, that is a very important. Like what I said, most of the cases that you do have a stable plan model. Okay, which means that most of the physical system, your open loop system is stable. But I did not exclude the case that the open loop system is not stable. We do have the physical system, the open loop system, it's not stable. Okay, so just be careful about that. And also, this one, this simplified Nyquist stability criterion actually can give us introduce another very important, concept, which is the stability margin. Okay, because you know what? Because you see right now we can simply just use if the Nyquist plot is gonna encircle this -1,0 point or not. So then one good question is that if we try to modify the G of S's Nyquist plot, well, we can only have two ways to modify it to affect the Nyquist plot, right? Magnitude and the phase. Okay, so if you look at this figure here, okay, if you look at this figure here, this is the Nyquist plot of the G of S. So you want to modify the plot, you have two ways, either magnitude or the phase, all same time. You change the magnitude and the phase same time. So you can see that when you change the magnitude, then the magnitude is going to be expand or shrink. Okay, either expand or shrink. It depends on, for example, if you apply the kg to it, and depends on the k is larger than 1 or less than 1, then you're going to expand or shrink the magnitude. So I talk about this, right? So if k is larger than 1, let's say if you apply the k, because the k is a pure gain, it is purely a gain, so it does not affect the G of S's Nyquist process phase. Okay, it does not affect the phase, right? So in this case, it will expand the plot radially. Every direction, it's going to be expanded at the same times or shrink same time. Depends on the value of the k. So if k is larger than 1, then you basically will push this point to the left, right? If k is less than 1, then you are pushing this point to the right. Well, this is because we are evaluating the plot along this direction. Okay, right? I mean, each direction, it's going to be expanded the same times, but my major concern is along this direction. This is the -180-degree direction. -180-degree direction. Okay, right? right? Okay, you have the phase at the crossover. We identify this point, then we need to do the calculation. So how am I going to calculate this crossing point? Yeah, you see, we can actually set up the imaginary part of the g of j